My name is Jim Elsert. I'm director of the Sustainable Phosphorus Alliance at Arizona State University and moderator of this scientific session, Phosphorus and Climate Change, a Vicious Circle. Thank you for joining us. This presentation is one of 3 pre-recorded videos focusing on this important topic before all the panelists come together in February for a live discussion. In this video, Dr. Laura Johnson of Heidelberg University will be discussing how ongoing climate change can amplify losses of phosphorus and other nutrients such as nitrogen to lakes, worsening lake eutrophication and potentially creating an unappreciated positive feedback between nutrient loading and climate change. Midway through this video, Dr. Matt Schultz of the Sustainable Phosphorus Alliance will be joining Laura to further explore these findings and their implications.
Thanks, Jim, for that wonderful introduction. As you mentioned, today what I want to talk to you all about is how nutrient loading in Lake Erie is linked to eutrophication of Lake Erie as well, and how that might be in part driven by climate change. As you can see here, I just wanted to start by showing why we're talking about this issue in the first place. You can see that Lake Erie experiences very large harmful algal blooms pretty much every year that has been occurring through all of the 2000s. So these big blooms occur in the summer. This is the 2019 bloom. You can see it taking up a good portion of the Western Basin, basically making that beach there, that's Maumee Bay State Park, unswimmable. But in Lake Erie, algal blooms are not necessarily a new thing. Historically, algal blooms plagued Lake Erie through the 60s and 70s, and the lake largely recovered into the 1990s. And then this is really a re-eutrophication of the lake that I want to be discussing a little bit today. So you can see the picture down there that's showing a photo from 1971 of the types of algal blooms that were present then. Luckily, over this whole period of time where we used to have blooms, they basically disappeared. And when they returned, we've been monitoring nutrient loads that are going into Lake Erie from most of the major tributaries at Heidelberg. And you can see here that we've got lots of dots on this map, so lots of different stations that we're monitoring. But our 2 longest term stations are the Maumee River and the Sandusky River. Those are the 2 black dots. So we've been monitoring there since 1975. So we're on our 45th year. Over 45 years of sampling for those 2 stations. Now, if you went to any one of these stations, basically what you would see is a building beside a river. We're pulling samples from these rivers 3 times a day using a refrigerated auto sampler. We retrieve them weekly, and then we bring them back to the lab for analysis of all major nutrients, so various forms of nitrogen and phosphorus, as well as suspended sediment. Today, however, what I'm going to focus primarily on is the Maumee River for 2 reasons. First of all, the Maumee River is one of basically the largest input into Lake Erie and to any of the Great Lakes for that matter. But also it's got trends that are very similar to other watersheds in the Western Lake Erie Basin, like the Portage River, the Sandusky, as well as River Raisin. So what are we seeing in the Maumee River? We've been monitoring there for quite some time. This is showing nutrient loads of total suspended solids. This is only for the March through July period. And you can see that each bar here is a different year, and the line is the 5-year running average. So for total suspended solids, what you notice that the concentrations, the loadings were quite high early on in the period of record, and they largely decreased through the 90s into the 2000s. And then there's been a slight increase, but not a whole lot of change since then. The decrease that occurred through the 80s and 90s is largely associated with erosion control practices that were put into place to keep farmland on the farms instead of in our creeks and rivers. And they were fairly successful. When we look at nitrate nitrogen over time, what we instead see is sort of an oscillating pattern that's being driven in part by flow, but then also by concentration patterns as well. What you do note, though, is the 2000s, there was a pretty sharp decrease in nitrate nitrogen, and there hasn't been a whole lot of change since then. However, the thing to note with nitrate nitrogen is that these loads are really high. We get fairly high concentrations, up to about 20 milligrams per liter each year, but they're also hugely variable. In drought years like 2012, you basically can have almost no loading, whereas we can have very high loading at other very wet years. The one constituent that has changed that corresponds with our observations of changes in blooms in the lake is dissolved reactive phosphorus. And you can see that dissolved reactive phosphorus had very high loads in the 70s and 80s that dropped down in the 80s and 90s. And then since about the late 90s, we've seen a steady increase in loading of dissolved reactive phosphorus over that whole period of time. The gray line on this chart is the target load that we want to get below so that we have a minimal bloom each year. And so you can see here that in the 90s, loading was actually below that target line, so that shows that these targets line up really well with our historical observations. So why am I focusing so much on March through July? That might be a little bit weird. You might be thinking I should be looking at a full year. And that's because if we look at March through July, especially in our recent years in the 2000s, that loading is really closely correlated to the size of the bloom each year. And the size of the bloom is being shown here through satellite imagery. Basically, this is called the cyanobacterial index, and that pulls together both the intensity of the cyanobacteria as well as the extent. So you can see that at the very low end of the spectrum, we have 2012, which is the very low end of the bars here as well. And then at the very high end is 2015, which is the highest DRP loading that we've seen through this period of time in our whole period of record. So the next question is then, well, why is dissolved phosphorus loading increasing? Why is it increased and over that period of time? And if you look at the 2000s to 2020, you can see that this pattern looks really similar to stream flow discharge. So basically, our loading in most recent years is being almost entirely driven by flow. Whether if we have a high flow year, we have a lot of loads versus a low flow year. And this flow has been increasing primarily because general increases both in total precipitation as well as in heavy precipitation events in this region. But what's interesting here is that we know that loading is in part driven by flow, but it's not entirely. And Helen Jarvie was able to take our data and do some interesting comparisons here, where essentially what she did was she applied a concentration versus flow model from the 80s to the flows we're getting in the 2000s to see how much of the contribution of increased flow contributed to this increased loading, and basically found that these lines didn't match. You can see the dashed line isn't nearly as high as the solid line here. And so what this implied was that higher runoff volume was really only accounting for about 35% of the increased load, which tells us that the remaining 65% of that increased load is actually because of changes in concentration, the other factor in loading. And that change in concentration has been largely attributed to changes in agricultural practices. So you can see this concentration plot that looks very similar to the loading plot that shows that same U-shaped curve and dissolved phosphorus concentrations now. But since the 2000s, those concentrations have really leveled off at higher than desired levels. So then that's where the flow is really driving what we've been seeing in the recent 2 decades. What agricultural practices are we talking about? Well, those same soil erosion BMPs that were so successful at reducing sediments as well as particulate phosphorus are also those that might be the reason why we're seeing the increased dissolved phosphorus loading. So the switch from a very intensive tillage to more of a conservation tillage with a high residue management is often paired with surface application of phosphorus. And those two things are leading to essentially some leaking of phosphorus that's coming through our fields, actually through some of our subsurface tile drainage. So we can take these data and put them into watershed scale models to predict the effects of climate change, and especially interested in looking at how climate change affects mid-century. We get differing results. You can see that there's been a number of studies that have come out that give us slightly different answers to this question. One I'm focusing on here is from Rem Confessor from Heidelberg, so it's from our group. And basically what he found was that future climate scenarios increase precipitation amounts and intensity more, also increases temperature, but those increases in precipitation led to increased runoff. And in this figure here, what it shows is that increase in runoff basically doubles the chance of having a very severe bloom by mid-century. So you can see that our historical observations are that about right now, we're around 12% chance of having a very severe bloom in a given year. By mid-century, it would be 24% chance. But in contrast, Margaret Kalsick from Ohio State did a similar approach, and what they found using multiple different models here is that even though precipitation intensity and amounts increased, there's also associated decreased snowfall and such a high increase in evapotranspiration that in fact, if you looked at any form of phosphorus, total, dissolved, spring, or annual, the phosphorus loads actually decreased by mid-century instead of increasing. And so I think this really highlights how difficult it is to put all of these different scenarios together when we're trying to think of agricultural practices, climate practices, and what's going to actually happen in the lake. But we might be able to learn something from some of our recent years. And one I want to highlight is 2019. 2019 was an especially wet year. And basically what ended up happening is it rained from the November of 2018 all the way through June of 2019. And that prevented a lot of planting in the Maumee River Basin. You can see from this vegetation index that by August, we can still see that like half the ground is still unplanted compared to 2018, where most of the ground is planted except for the cities. This large amount of unplanted area basically led to much lower phosphorus application throughout the whole watershed. And in response to that, what we ended up finding was that dissolved phosphorus loads were far lower than what we would have expected based off of flow. So this figure is showing load versus discharge or stream flow discharge. And you can see that from 2000 to 2018, there's a really, really good relationship between loading and discharge. And then 2019, we fall way off of that relationship, getting closer to those two gray lines, which are the concentration loading targets for the lake. This resulted in a lower than potentially expected bloom based off of flow. So you can see this is bloom severity index, which ended up being a 7.5 in 2019, which is about what we predicted. But if we had based that off of flow, which you can see was super high in 2019, we would have expected our third largest bloom on record. So let's pull all this together. Basically, what I've showed you is that eutrophication in Lake Erie is associated with increased dissolved phosphorus loads that are occurring between March and July, and that these increases are in part associated with higher flows, but then also in part associated with changes in agricultural practices that happened in the 80s and 90s. If agriculture can continue as it does today, then our future climate scenario predictions can give us some mixed results. In some cases, it appears that we might have increased bloom severity associated with these runoff events, but that study also has shown that they can be very well mediated with appropriate practices, the ones that are very popular today. In another study, it found that these needed reductions in nutrient loading might be easier to attain because of increased evapotranspiration and overall lower loading. However, what 2019 showed us is that the inability to farm in general might also reduce nutrient loads, and that might be something that's very difficult to predict when that will or will not happen. But there are a couple of caveats that I want to point out. First of all, the toxicity of these blooms, these are harmful algae, it's microcystis blooms that produce microcystin. The toxicity appears to be more closely linked to nitrogen availability rather than phosphorus loads. So while phosphorus is telling us how intense the bloom is and how big it is, it's not telling us as much about toxicity. So nitrogen will continue to be very important and something that needs more study. The second thing is I didn't talk a lot about the dead zone in the central basin of Lake Erie. So there is a very large hypoxic area that's tied to phosphorus loads over multiple years. So internal loading of phosphorus that's coming in. And so when we have these very large years followed by droughts, those drought years, although you would think that they shouldn't have as much input into the lake, they can oftentimes have a very big dead zone because of the quiet nature of the water during those periods of time. And so with that, I wanted to acknowledge all of the funding, both for our monitoring program, as well as for some of our research projects to help understand these different things. This is my contact information if you have any further questions.
Thank you, Dr. Johnson. Now Dr. Schultz will join the conversation. Welcome back, Matt.
Great, Laura. Thanks so much for that talk. Just a few responding questions for you. The first one is, we may have to implement more agricultural best management practices to offset climate change. And I'm wondering how widespread implementation would need to be. Are the current farmland fluxes the result of a few bad actors, or is the problem more systemic?
Yeah, that's a really interesting question that I don't have a perfect answer for. If we look at across the Maumee watershed and parts of the Western Lake Erie Basin at different sub-watersheds, it looks like oftentimes the exports are quite similar. There's a few differences here and there, but in general, it seems like wide swaths of land are exporting similar amounts, especially of dissolved reactive phosphorus. And so the question is, well, does that mean that we see those types of very similar exports everywhere? Well, in fact, what we've noticed is that when you get to the farm scale, when you're looking at soil phosphorus just across the different farms, what we've noticed is that there's an awful lot of variability there. A lot of it is associated with like old barnyards where livestock used to be, and over application of manure. And so there can be places where there's, even within one field, some places that are really high levels of soil test phosphorus and other places that are really low. And so what we are thinking right now, and there's like I said, there's studies that are going in to better investigate this, is that in fact, there's probably wide areas that are exporting very similar amounts of phosphorus, but when you really zoom in, there are hot spots. It's just at a subfield scale, which makes it harder to manage in general.
Yeah, sure. And so how much of the problem today is driven by past applications of phosphorus that have been stored in the soil, so this so-called legacy phosphorus, versus current applications, and how do the mitigation strategies differ for the two?
Yeah, right. So in the 2019 study, that indicated that potentially up to 30% of phosphorus is coming from recent year applications. However, what you have to remember from that 2019 study is that it's not like the entire watershed stopped applying phosphorus. All we could have quantified was about 46% of phosphorus was sold. So what that implies is that that certainly recent year applications are having some effect, and that we think that it doesn't have to necessarily do with the soil test levels in that year. But I think, that might be an overestimate for various reasons for a given year. On an edge of field level, I think that their studies are showing it's probably more like 15 to 20% is coming from recent applications. What that tells us is that a vast majority is coming from other years and might be applied with, or coming with like how we're managing our phosphorus in our soils, right? We're managing to maintain a certain amount of phosphorus that's available for crops, which then can run off with any rain event, really.
And then about the mitigation piece, are there differences in how you mitigate the two types, the legacy phosphorus and sort of the more recent applications?
Yeah, absolutely. If we're talking about losses that are occurring with application, then we're talking about things like where are we applying, at what time, how application is occurring. And so there's a lot of studies that's been supported both through observation as well as through modeling efforts that are indicating that if we can get phosphorus off the soil, if we can, or the surface of the soil, if we can inject it below 2 inches, that we probably would get less loss of that freshly applied or overall applied phosphorus. We're talking about really high soil test levels, which we don't see very commonly throughout the Western Lake Erie Basin, but they do happen. In that scenario, really we need a lot of patience and probably some smart engineering. So when it comes to a lot of patience, I mean, usually our only option is crop drawdown. So you just keep growing whatever you're growing and you harvest away your phosphorus, and eventually you lose that bank of phosphorus. That can be a very long process. And so there is some really interesting work happening in this region looking at phosphorus filters that would go at the edge of the field to actually remove that phosphorus before it get off the field and into a ditch. And I think that, using that in these places where we have moderate to high soil test levels and losses is what makes the most sense economically, at least.
And those filters would be installed on tile drain systems, right? Is the idea?
That's the idea, exactly.
Yeah, okay.
Yeah.
And do you see evidence that the jurisdictions charged with managing the Great Lakes water quality are considering climate change in the policies that they're developing?
Well, it's a little tough because right now we're just trying to make any progress that we can in terms of improving water management and water quality. I would say that we can see hints of this certainly when we look at the targets that we have for Lake Erie. For instance, we talk about things like, well, we expect to meet this target load, but in 90 percentile flow years, we might have flows that are so high that we're going to exceed it and farmers can't control it. Well, that's the anticipation of a climate change issue, of the fact that we might be seeing such high flows that there's not a whole lot anybody can do. On the flip side, I also would say that when you look at management, we talk a lot about managing the phosphorus itself, but there's a lot of talk about managing water. Like, how can we keep water on fields instead of in our streams and rivers and out to the lake? And in doing that, that's also, I think, talking about mitigating factors that are beyond our control. If we can improve soil health and we can improve drainage water management to keep water put, then that means we're not going to get those phosphorus losses because it didn't actually make it all the way to the stream.
Yeah, it makes sense. Well, great. Thanks for answering those questions, and thanks again for your presentation.
Yeah, thank you.
Thank you again, Laura, for your presentation, and thank you, Matt, for deepening the discussion of this important material. I want to remind everyone that this is just one of 3 spotlight videos focusing on this important work of the speakers before all the speakers come together in February in a live panel dealing with phosphorus and climate change, a vicious circle. Please check the AAAS annual meeting website for the panel's date and time. Again, thank you, Laura, thank you, Matt, and thank you to the audience. We'll see you live in February.